let's do 3 examples of looking at similar triangles. So example 1 is on the right here. We're given that segment AC is parallel to DB, and as it looks like ALB is one straight line, CLD is one straight line. And the question is, can we say that these 2 triangles on the left and right are similar? And can we say that precisely? If so, and I claim yes, they are going to be similar. And you might want to stop and think about why that would be true. We definitely have some angle congruences. In particular, at L, we have vertical angles. And so angle ALC and BLD are going to be congruent. Let me indicate that. So that's one pair of angles that are congruent. And then I claim we have another pair of angles that are congruent. Well, we really can pick, have our pick of a couple more pairs. For example, if I look at LAC, the angle right in here, then that's opposite interior angles with these parallel lines to DBL. So those are congruent. Let me mark those. So let me put in here exactly what we're saying. We're saying that angle, let's see, it was ALC is congruent to angle DLB. That was the first, that was the vertical angles. And then angle LAC is congruent to angle DBL. And that was opposite interior. And so we've got our AA, which is enough for AA similarity, but we really want to say it carefully. So we do have triangle ACL. Oops, there we go. Is going to be similar, not congruent. They're not the same size, clearly, to BDL. And I've got to make this really precise. I've got to make sure that they match. So that angle at L, yes, that was something that matched over here and over here. The angle at A matched the angle at B. So that's why the A is matching the B. And then if we wanted to, we could also observe that it has to be true that the angle at C, in other words, like ACL, has got to match the angle at D over here, BDL. But we didn't need to do that because we get that for free from 2 angles. We get the third one. So that's the precise similarity statement. And you do want to make sure you're making that correct, because otherwise you're just saying something that's incorrect and you're going to have wrong conclusions. Okay, so now that we know they're similar, we could actually use that. Notice I've got 3 lengths measured here, and I'd like to be able to predict what the length of AL is. And of course, that's where we use a proportion, that anytime you have similar polygons of any type, then you know that they're similar, and that's what we've gotten from AA. Well, let me put that here, by AA similarity. We can set up a proportion. So we could do it in a couple of ways. We could say that AL, which is what we want to figure out, divided by CL. So that is an internal ratio of lengths in the left-hand triangle, and we can figure out what that corresponds to by thinking about the vertices or the angles. AL is the one opposite C. That's the one that's still unmarked. So that should correspond to the one that's opposite D. So that'll be LB. And CL is the one that's opposite the double hash marked angle. And so the one over here that's opposite the double hash marked angle is LD. So that's equality of of shape numbers, shape ratios, I guess I want to say. And that's one way we could do it. And we can put in the 3 known quantities and solve. We could do that in a minute. But I also want to say you could also do it as AL over LB. So AL is again opposite to angle C here. That's corresponding to the LB, as we just mentioned. That's going to be a scale factor. That's the scale factor that turns the right-hand triangle into the left-hand triangle. That should be the same as the scale factor that turns LD, and again, that's opposite the double marked angle, into CL. That's the corresponding side of the big one. And so that's going to be CL over LD. Now notice this is exactly just what happens if you take this proportion and you do the switch the means property of proportions. But I like to point out, like I did in the previous videos, that this is equality of scale factors between the triangles. So they're both good way to think about it, but this quantity is a measure of one measure of the shape of the left-hand triangle, and it matches the corresponding measure of the shape of the right-hand triangle. This is a rather different perspective here. This compares the two triangles. What mystery factor is going to scale one part of the right-hand triangle to get the corresponding part of the left-hand triangle? That had better match the scale factor that takes any other part of the right-hand triangle and scales it to get the left-hand triangle. So we can use either one. I guess I'll just use the bottom one. And so AL, which is our unknown, over 2.74 equals 3.74 over 1.96. So AL is going to be 2.74 times this ratio. And then we'll just let the calculator do that. And so that turns out to be 5.2, it says 5.23. No point in reporting fictional decimal places. So that's an example of carefully proving the similarity of two triangles and then using the proportionalities that we get to conclude something about one of the lengths of the triangles. And we'll do the other two examples in a second part of the video.